Okay, let's begin. So it's a great pleasure to have Andrew Schopieray from the University of Alberta to tell us about his recent work on categorification of integral group rings extended by one dimension. Andrew, please.
Thank you, Elon, for the invitation, and the rest of the organizers, and BIMSA for hosting this seminar. And it's a great idea that Elon just saw my preprint appear on the archive and invited me to give a talk about it. I think that makes for a much better talk when I already know what I'm going to speak about, and it's something that clearly I've been thinking about very recently since I just put this paper up. So I've put the archive identifier on the title page here, and I'll also share my notes or my slides, I should say, when the talk's over. So my talk's going to be split into 3 parts, and the first 2 are going to be very understandable by most anyone because they're mostly about rings and very basics of what is going to be called categorification. And then the third part is going to be a little bit more aimed towards people who are already trying to think about these things, but most of the talk should be accessible to almost everyone. So in my first part, I just want to discuss what I mean by categorification, and I'll describe this by example, because hopefully these are some examples that everyone has seen before. Let me make my font just a little bit bigger here. So let's take, for example, the integral group ring. So this is sort of the formal sum of elements of a finite group. So I like to think about this as just these little dots floating out in space that represent the elements of this finite group. And this ring is just formal sums of these. So we have an addition, which is just purely formal. So G plus H is just G plus H, it's just a formal sum. But we also have a multiplication for this ring, which is just the group operation. So the other structure that we naturally have, because this is a group, is we have a unit for this multiplication. So I usually like to call this E. So this is the multiplicative unit. And another special thing about groups, one of the only special things about groups, is that we also have this inversion, right? So I can take an element of my group and I can invert it. Okay. This is just the inversion from our group G. So categorification is essentially trying to find a larger structure that has a lot more data associated to it that represents this ring as like a skeleton. I like to think of these rings as skeletons and the categorification as all the other muscles and organs and parts of the body that make everything work. So this is just a very rough outline of what we want. So these integral group rings, we can categorify in a very easy way. So we know that there is a category, which I'm going to denote by vec G. So this is going to be the category of finite dimensional, and let's just call them complex vector spaces for now. So we'll work over the complex numbers just to make things easier. And this is a semi-simple category. So its set of simple objects look shockingly like our original group, except for I'm thinking about them as sort of one-dimensional vector spaces. So just our base field indexed by the elements of our group. But this category, this category of finite dimensional complex vector spaces graded by the group G, has a lot of the structure that the original ring has. So rather than having just formal sums of elements of our group, we actually have a direct sum of vector spaces And instead of having an operation for our group, we can take tensor products of vector spaces, since this is just linear algebra. And this tensor product has a multiplicative unit, which is just our base field itself, or you can think about it as our base field indexed by our unit of our group. Okay? So this is our tensor unit. And we even have this notion of inversion in this category, which is looking at a dual vector space. So if I have any sort of vector space, I can look at its dual vector space. And since we're in finite dimensional vector spaces, I get something very nice again. So I'm staying inside of this nice category. And these are all the properties that the original ring had, but we have one additional thing. We have all of this extra data. It's not much extra data in this case, but we have data of maps in between these elements. Okay. So in the categorical land, we have this hom set, this set of C-linear maps in between these vector spaces. Since they're just one-dimensional vector spaces, they're not very interesting in this case, but that's sort of a lot more data than we had in the original ring. So when I say categorification, what I want is I want a category that has all of these addition, products, multiplicative unit, this inversion in a categorical form. And when I forget all of the categorical data, so you can think about this as passing to the Grothendieck ring of this category, I sort of retrieve the original ring that I had. Okay. So this is a categorical enhancement of some very combinatorial or very algebraic object. So another example is our character ring for our finite group G. So you can think of this as composed of our irreducible characters. Maybe I call them chi. Which form a basis for the space of class functions, et cetera, what we learn as undergraduates. And these irreducible characters have all of the structures that our integral group ring had. I have a sum, which in this case is pointwise addition of these functions. I have a multiplication, which is pointwise multiplication of these functions. I have a unit, which I'm not sure what I would use for my unit, just trivial maybe. I have a trivial character, which acts completely trivial, sends everything to 1. And I also have inversion, in this case, takes the form of complex conjugation. So rather than doing an inverse, I'm conjugating this character. So how do I categorify the notion of this character ring for a finite group? Well, I have to be a little more clever than using vector spaces, but as we all learned in algebra, there's a nice category, this representations of this finite group, which realizes this ring very nicely. So rather than having irreducible characters, I have representations, I don't know, maybe size. I have these irreducible representations of G. Okay, and what can I do with these representations? Well, just like in the vector, basically, these are vector spaces with an additional, action of our group G. So I can still take our direct sums. I can still talk about tensor products of representation. I have my trivial representation, which acts as a unit. So this is our tensor unit. And I have these dual representations which exist in a, sorry, I'm running out of space here, which exist essentially because we have this Hopf algebra structure on, our group algebra itself. So all of these structures really are from the case that our group algebra is a Hopf algebra. Okay. So these correspond to the properties that we wanted in our original character ring, except we have something a little more interesting in this case, which is all of the intertwiners, all of the maps in between these representations. So in this case, the spaces of intertwiners between finite dimensional irreducible representations of G are much more interesting because we have very large irreducible representations. So they have lots of very interesting endomorphisms, for example. And we have lots of different morphisms going in between different representations as well, very non-trivial ones. So this is a lot more data than is contained in the ring. But just as before, when I forget all of that extra data in green, I just look at the Grothendieck ring of this category. I get back to my character ring. So rep G is a categorification of this very nice ring that I started with, the character ring for G. So this is what I mean by categorification. So if we want to write what the entire class of rings that I'm interested in categorifying are, things that formalize these properties in these two examples, then we get what's called a fusion ring. So a fusion ring at the outset is a ring. So I have my addition and I have my multiplication, and I want my multiplication to be associative and unital. So I have a unit for this ring, and I want it to have some sort of a basis. So I want it to be free as an abelian group. Okay. And this is supposed to replicate the idea that I have this semi-simple category that I'm looking for, and I can only need to discuss a finite number of sort of basis elements to describe the multiplication for everything else. So I want to include as part of the data a choice of that basis. Okay. So I want to take some distinguished elements, one of them, which is my tensor unit. And I want to choose that basis so that I have a positivity and integrality constraint. And this corresponds, of course, to the fact that when I am going to be tensoring things in my category, I want to get positive integer sums or non-negative integer sums of those simple objects. So this has a very categorical reason why we want to stipulate this. Now, the last one, just so I don't end up with integral group rings and nothing else, is I don't want to force my category that I'm getting into to have all of the simple objects be invertible, like in our group case. Really, I just want something that's close to invertibility, but not quite. So what I want is I want this duality, which is almost like inversion. So when I take an element and I tensor it with its dual, I want to get the identity appearing, but possibly I have some other noise. Okay. So I'm not just getting the identity on the nose, I'm getting the identity with multiplicity 1 and possibly some other basis elements. Okay. But if two things aren't dual to one another, I don't want to see the identity appearing. So this actually makes sense for our character ring and our category of representations, because if I take any irreducible representation that is dimension larger than 1, for example, maybe the 2-dimensional representation of the symmetric group on 3 elements, clearly I'm not going to be able to tensor that with anything and get the identity, because I don't have a representation of dimension 1/2, for example. But when I tensor that representation with itself in that very specific example, I get the identity with multiplicity 1, and I get the other representations of S3 as well. So that's our duality for that particular representation in this category. So these are the types of rings that I want to understand. And you can study these rings just by themselves. They're actually a very interesting class of rings. So you can study them, you can study their representation theory, and this is a very interesting subject by itself. But I was trained in a more categorical setting. And so what we're going to be doing in this talk, and what I've written in my paper, is trying to look at the categories that realize these very particular set of rings. So the categories that we're restricting ourselves to are basically just enough axioms so that when I forget all of the categorical data, I get a fusion ring. So that's the easiest way to describe it to someone. But if you want to write down the axioms, you need things like, you need semi-simplicity, for example, and semi-simplicity corresponds to, as I said before, this fact that our rings are free as a Z module. You need them to be C-linear if we're working over complex numbers, for example. So I have these nice home spaces, and et cetera, et cetera. I won't write down all of the axioms because it's not too important. Just think about these fusion rings with the addition of these nice home spaces. So in fact, most of our categorical data in a category, nothing's equal on the nose for the most part. Everything's only equal up to isomorphisms, but our choice of isomorphisms is very restricted for these fusion categories, in the sense that if I pick some very exotic isomorphisms, for example, between like X tensor or unit, that has to be isomorphic to X itself. If I pick some very weird isomorphism for this, then I can always find an equivalent fusion category where it's a very trivial isomorphism. There's sort of a canonical choice for all of these basic structure axioms that we have, with one exception. So the really important data of a fusion category, the very non-trivial part, if it's a fusion category, all this stuff is sort of decided for us up to some canonical equivalence. The only thing that is flexible in that sense are these associative isomorphisms. Okay. So really, if you want to create a fusion category, what you need to do is you need to find associative isomorphisms, or associators as some people call them, so that your tensor product has that associative structure. And the reason why this can be so difficult, well, you need a lot of conditions to be satisfied. You need to have these isomorphisms for every triple of simple objects in your category, for example. So already you're looking at the rank of your category cubed sets of isomorphisms, and they have to satisfy compatibility relations with all of the other structure in your category. So fortunately, ages ago, it was shown that really all you need is to solve what they call these pentagons. So I'm not going to write out the actual pentagon. I'll just draw a very small one. But these are the two ways that you can associate a set of 4 simple objects tensored together and move the parentheses from one side to the other. You can do that in 2 different ways. Okay? And all of these pentagons need to be commutative. So that's for 4 different simple objects tensored together. And so there's a lot of pentagons. And so this is not something that sort of grows linearly in difficulty as you increase the number of simple objects. This is something that just almost immediately becomes impossible unless you're very clever about how you're trying to solve these equations. So there's been a lot of great work done, possibly by some people in this audience even, on solving these pentagons, or at least coming up with more clever ways to realize solutions for them. So again, our categorification is starting with a fusion ring and trying to find a fusion category, or maybe multiple fusion categories that have a Grothendieck ring, which is our original fusion ring. So in the back of our head, there's always this forgetful part to go back. And if you ever get lost, just remember our two original examples, because honestly, in a lot of our work, these are the two examples that we understand the best. And so we keep going back to them for inspiration. Okay. So this is what categorification is. So let's look at more examples, because I gave you one categorification of the integral group rings, but there are lots more. And in fact, you can classify all of the categorifications for these integral group rings. So they're all equivalent to the category of finite dimensional, let's say, complex vector spaces, graded by your group G. But now that we know that there's this flexibility of these isomorphisms coming from the associative condition, we can tweak these vector spaces by that data. So I'm going to put a little omega here, and let's see what that omega data actually is. Well, it's isomorphisms between, let's just pick 3 elements of our group, F, G, H. And I need a map from, I'll be tedious and I'll write out the one-dimensional vector spaces, C, F, C, G, and C, H, all tensored together. And if I put the parentheses here, I need an isomorphism to the exact same thing with the parentheses moved. Okay, so this is the omega that I'm looking for, but this omega represents sort of all of the triples, F, G, and H, and I need some map in between them. But this vector space, this is just one-dimensional vector space, one-dimensional vector space, one-dimensional vector space. This is just another one of our one-dimensional vector spaces. This is just our C, F, G, H, whatever element of our group is, and exactly the same on this side. Since our group operation is associative, these are the exact same thing. So I'm looking for a map in between 2 simple objects in my category, and that's either 0 or that's going to be some non-zero scalar if this is actually isomorphic. Okay. So the data of this omega can be thought of as a map. I take 3 elements of my group and I spit out this non-zero scalar that corresponds to this isomorphism. So it needs to satisfy the pentagon equations, which are the consistency of all of these associators with themselves. And these pentagon equations, sorry, my pen freaked out there for a second. These pentagon equations imply that this omega is actually an element of H3 of G with coefficients in C, okay, or C star. So this is exactly what it means to be an associator for the category of G-graded, finite dimensional G-graded vector spaces over C. So you get something very nice and something that's very computable. So for instance, for a cyclic group of order P, there's actually P different categories, these vec G omegas that are inequivalent, but still categorify our integral group ring over that cyclic group. Okay. So it's quite interesting, this question of categorification, even for these most trivial cases, these integral group rings. So there's another way to think about these integral group rings, which is a little less intuitive unless you've studied the fusion categories before. So these integral group rings are characterized by the fact that the fusion matrices, so this is just taking all of those coefficients, which you get when you tensor two of the base elements together. Those fusion matrices are all permutations, because when I tensor or I take a product of G with anything in the group, I just get another group element. So this is very specific to these group rings. If I have something that is sort of more complex in the multiplication, I'm certainly not going to get permutation matrices in this way. So to describe specifically this complexity, how far away am I from being a permutation matrix, or how complicated are the products, the fusion rules, we call them in our fusion ring? We come up with a way of measuring that using the Frobenius-Perron theorem, which under the conditions of a fusion ring says that these matrices have a unique real maximal eigenvalue. So this eigenvalue is maximal in modulus. So if you have complex eigenvalues, then the maximal one is real and dominates the modulus of all the other ones. So this is sort of just the width of the spectrum of this matrix. And so the Frobenius-Perron dimension for the basis elements of the integral group rings, they're permutation matrices. So their eigenvalues are all roots of unity. So their Frobenius-Perron eigenvalue is all 1. Okay. So the simplest fusion rules, the simplest fusion rings that you could possibly look at are those such that the Frobenius-Perron dimension, this eigenvalue for the multiplication, is 1 for all of your basis elements. So these are completely characterized by this fact. So if you give me a fusion ring, basis elements are all 1, then you're an integral group ring for some finite group G. Okay. So really, we know the entire story. It's pretty impressive considering how hard it is in the general case. We know the complete story for fusion rings with a basis of elements of dimension 1. We know all of the rings, and we know all of their categorifications. So that's sort of where our complete knowledge ends. It ends very abruptly. So in my paper, as you can tell by the title, we want to extend this as mildly as possible so we can still say something very powerful about these categorifications. So if I take a number that's larger than 1, I want to know what can be said about categorifications of fusion rings so that all the basis elements are either 1, so they're acting by permutations on the basis, or they're this special number D. So don't treat this as a technical phrase that you should learn, because it's not a very good name for it, but verbally I might refer to these as 2-dimension fusion rings. So all the basis elements, they take a Frobenius-Perron dimension that's 1 of 2 values. Okay. It sounds a little too much like 2-dimensional to be a good name, but I might say this out loud by accident, so I want to warn you. So as I mentioned before, you're going to have some basis elements who have dimension 1. And so these are acting by the multiplication by permutations on the rest of the elements. So they're acting on the elements of dimension 1 by permutations. And all of these elements of dimension 1 are going to form a finite group, which we can call G with a little r next to it. So this is going to be the set of all basis elements of dimension 1. So this little GR also acts on the objects of dimension D. And this Frobenius-Perron dimension is a character of the group. It's multiplicative, it's additive. And so GR is just going to permute those objects of dimension D as well. Okay. So this is sort of, this GR is an important piece of data. It's this sort of subgroup of this fusion ring. Now, the other piece of information that's important is that this number D can't be incredibly complicated. So since this Frobenius-Perron dimension is multiplicative and additive, if I take any one of my basis elements and I multiply it by its dual, it has to decompose into basis elements from our basis, which all have dimension D or 1. So I'm going to get a big sum of basis elements of Frobenius-Perron dimension D, and I'm going to get some big sum of basis elements of Frobenius-Perron dimension 1. So if I look at the dimension of this as inequality, I'm getting that the dimension of this B times B star, so this would be, if this was a basis element of dimension D, this would be D squared. And then I would have some non-negative integer here, which is just the sums of, you know, how many of these elements appear in this sum times D plus however many objects of dimension 1 appear times 1. So this R here is just the number of elements of dimension D that appear, and this S is just the number of elements of dimension 1 that appear. So these are quadratic numbers. These are quadratic integers, in fact, that this D could take. So immediately, you know, D could be any positive real number greater than 1 at the outset. But in fact, we're really just looking at quadratic integers. So we're looking at a very small subset of possibilities. And we haven't even started looking at much of the structure. So after we know that these are quadratic integers, these two-dimension fusion rings, if you will, have sort of two classes. There's a natural bifurcation that happens with these fusion rings. One is that the number that you chose, this quadratic integer, is truly quadratic. You've picked something where our equation up here is irreducible. So I'm not getting an integer. And in this case, there's a lemma in my paper. In the irrational case, this implies that my group of invertible objects, my group of objects of Frobenius-Perron dimension 1, acts on the rest of my basis. So my basis kicking out those elements transitively. So this is very powerful. So really, how I can interpret this, since I have this two-dimensional, or see, this two-dimension fusion ring, I can just write this as I have one orbit, one GR orbit of invertible objects, and I have one GR orbit of non-invertible objects. So this is much easier to write as the set of orbits of my basis when acted upon by my group GR is exactly 2. Okay. So the irrational two-dimension fusion rings are actually 2 orbit fusion rings. Okay? There's only 2 orbits under this action. So this is completely antithesis to what happens when D is an integer. So when D is an integer, this definitely does not happen. Our number of orbits could be almost anything. This is just some integer greater than or equal to 2. Okay. So you can identify which case you're in if you know whether D is a rational or an integer by looking at how R and S compare to one another. For an example, if your second dimension, your non-trivial dimension, is an integer, then that R, the number of invertible objects that appear, or sorry, the number of non-invertible objects which appears in B tensor B star has to be strictly less than the number of invertible objects. That's very easy to show. I'm sure you could prove from this equality that that has to be the case. And so if you're a rational, that implies that your R has to be greater than or equal to S. So there's all of these different results that show that these 2 cases, these 2 classes of 2-dimension fusion rings are very different. They're very different in behavior. So to give you an example, just to show that, this truly is a very different set of cases, we'll look at some integral ones. Because the irrational ones, the non-integral ones, they're 2 orbits. There's just 2 orbits under the action on the basis by the invertible elements. But if we're integral, let's see what happens. So let's look at the character rings for the dihedral groups, Dn. So when n is odd, my set of invertibles, I think there's just 2 of them. So I get a cyclic group of order 2. And when n is even, I get 4 of them. Okay. So I have a very small set of invertibles. So if the non-trivial dimension in this case was irrational, then these fusion rings would be very small because I could only have at most 2 irrational dimensions, 2 basis elements with irrational dimensions in the first case. And in the second case, I could have at most 4, since this group has to act transitively. But as you know, there's a lot of other elements in this ring. So for n odd, I think we have, it's like n minus 1 over 2, degree 2 characters. And in the even case, I think it's like n minus 2 over 2. Don't quote me on that. If that's not correct, it's very close. Okay. So if n is very large, then clearly these groups are not acting transitively on those remaining degree 2 irreducible characters. So in fact, you can make it as bad as you want. If n is incredibly large, basically almost the entire ring is separated by orbits of these invertible elements. There's just hundreds and hundreds and hundreds of them, as many as you want. Okay. So this is the complete opposite of what happens when your non-trivial dimension is irrational. So these irrational 2-dimension fusion rings should be thought of as something that's much easier to describe, actually. So the other family of 2-dimension fusion rings that produces examples of both of these is actually the case where you have your group of invertible basis elements, which are acting by permutations, and you have exactly 1 non-invertible element. So we call these near group historically because they're basically as close to just an integral group ring as you could possibly be. So I'll write this out in full. These are fusion rings with a basis, with a unique non-invertible element. And typically, I don't know how it became commonplace, but we called this rho, okay, this unique non-invertible basis element. So all of the data of the fusion ring is essentially determined. I have my underlying group. So there's a finite group G. And this is our set of invertible elements for this two-dimension fusion ring. And I know how the duality works for all of these invertible elements. And since duality preserves dimension, this unique non-invertible basis element has to be self-dual, we would say. So it's its own dual. And so the only thing that is remaining is what happens when I multiply rho by itself. All of the invertible elements have to act trivially because this is the only object of its dimension. So the other piece of information is this multiplicity, which I'll use L to describe, of this element rho. And from the axioms of a fusion ring, I actually have to get every single element in my group in that sum as well. So the two pieces of data are my finite group G and this multiplicity right here, this L. So if I want to describe a near group fusion ring, I'll often denote it, as I do in my paper, as just a ring, R for ring, associated to my group G and this integer L, okay? This non-negative integer L. So if you do read my paper, this is used throughout the paper. So all of these are two-dimension fusion rings for extremely trivial reason. And so they fit into what we've been talking about above. But these have actually been studied since before the term fusion category really even existed. So in the 1900s, the late 1900s, Tambari and Yamagami proved that if I set my coefficient to 0, so when I square my non-invertible element, I just get the sum of the group elements. They actually solved the associative constraints. They solved the pentagons, if you will, and proved that every single one of those rings is categorifiable. So we're actually getting this huge infinite class of categorifiable rings with the caveat that G must be abelian for that to be possible. So that's a bit of a surprise. So I can only categorify the near group ring with coefficient 0 if my group is abelian. So we're already seeing that something interesting is happening here. So not all of these near group fusion rings are going to work. So shortly after, and then much later in more detail, oh, and I should say, I noted that this was about 15 pages, this original paper, because I want to show sort of the jump in complexity that happened after this point. So shortly after, Masaki Izumi described a more general way of constructing categorifications when this coefficient is much larger than 0. And combining these three papers that I'm referencing right now is already over 300 pages of material. Okay? And really, it's just to construct a finite number of examples. So the difficulty, as I mentioned before, is not linear in growth. It just grows astronomical rate. Okay? And another piece of historical work in this direction was by David Evans and Terry Gannon. And they use Izumi's methods and some of their own to construct categorifications of near group fusion rings for cyclic groups where the multiplicity is exactly the order of the group. Okay. So this was not done for all of these fusion rings, because the solutions, finding solutions to these equations, as I said, it grows in complexity very quickly. So they did this for small groups. I think in this particular paper, they went up to like 13 or something like that. And I think one of Terry Gannon's students went up to like 30 at some point, but you're pushing computational ability at that point. You really need to do something that's more clever if you want to do this for an infinite family. And that paper was about 50 pages. So when L is 0, we're at 15 pages. When L is larger than 0, the story's not complete, but we're already over 350 pages of material on it. So this is a very difficult question. So some key observations that Izumi and Gannon and Evans made sort of all simultaneously, and then were sort of verified a little bit later on. Oh, and I should note that before I move on, that all of these construction methods from 2000 forward have an additional structure involved. So these all involve a unitary structure. So this unitary structure is additional to the axioms of a fusion category. So in fact, unitary fusion categories are probably a very small subset of all fusion categories that exist. So when I say that they constructed these categories, they constructed very, very special categorifications of these fusion rings. Possibly there could be some categorifications that aren't unitary as well. So even with all this work, we still have this additional structure to worry about as well. But the following facts, these are true with or without that assumption. So for instance, if I find a categorification for my near group fusion ring, then it's going to be something that's very close to unitary, like I was just discussing above, but not quite. Now, I won't go into the details about this, but basically this means that your ring's dimension, your ring's concept of dimension, which comes from these Frobenius-Perron eigenvalues, coincides with a more categorical notion of dimension, which comes from taking traces of endomorphisms in your category. So that's not to say that all categorifications have to be pseudo-unitary, but if it's categorifiable, you can always just assume without loss of generality that you've picked this very nice one. So this is a very technical result, but it makes a lot of work a lot easier. So there are other things that sort of prevent the near group fusion rings from being categorifiable. So for instance, if you pick a G and an L, such that the near group fusion ring is categorifiable, and your non-trivial dimension is irrational, then your order of the group has to divide that multiplicity. Okay. So for a very large group, I don't know, the monster group or something like that, there aren't very many small L's that you could pick that actually have categorifications. So immediately you've eliminated a ton of near group fusion rings from being categorifiable. And also, if your non-trivial dimension is irrational, if you find a categorification, then that means that the group that you started with is abelian. So just like in Tambara and Yamagami's paper, where the multiplicity was 0, in fact, if your Frobenius-Perron dimension is irrational at all, your group has to be abelian. Okay. So now if I pick an irrational dimension and my original group was non-abelian, none of those work. So our list is slowly dwindling for which of these near group fusion rings could actually be categorifiable. Now, countering that point, if we look at when the Frobenius Perron dimension is an integer, so where that L is less than the order of the group, I find actually that all of the possible near group fusion rings which are categorifiable are non-abelian. So these abelian groups that are categorifiable, they correspond to sort of the irrational non-trivial dimension. And these integral ones correspond to the non-abelian groups, with this one exception of G-1, which sort of falls directly in between those two cases. So there's an incredible amount of restrictions on which of these rings are categorifiable. So just to reiterate, when we started with the integral group rings, everything was categorifiable. It was just a paradise. Everything that you looked at, you could find multiple categorifications for. Now I add one element that is an invertible, and immediately almost any given near group fusion ring has no categorification attached to it. Okay. Where, random is more metaphorical than anything. If you just drew one out of a bag, there's no chance that there's a categorification attached to it. Okay. So what I wanted to do was take these very basic results and I wanted to generalize them just to fusion rings where there are two dimensions. So I'm not just looking at near group, I'm looking at some set of invertible objects and then some huge set possibly of objects of another dimension D. And the reason I did that is because you'll find that most of these results hold in the exact same way. So to discuss the results, you actually need to look at one piece of structure that's sort of hidden in the near group case. So if I have a two-dimension fusion ring and my invertible objects act transitively on the non-invertible objects, which has to be the case when your dimension is irrational, for example. So this is not a very strong condition. I'm basically missing out on things like representations of dihedral groups, for example. Then I can look at the stabilizer of my invertibles acting on my non-invertible objects. And I find that actually these stabilizers are all equal. So there's actually this canonical subgroup, which ends up being normal. It's a normal subgroup of my invertibles, which is the stabilizer of any given non-invertible basis element. So I'm going to call this canonical normal subgroup H. So this is just as important as that group G R of invertible elements. And the reason why that doesn't appear and why it's not important in the near group case, it doesn't appear in any of these results, is because it's actually hidden. It actually is the group G, since all of the invertible elements have to act trivially on that row. So this is an additional piece of information that's going to make these statements slightly more complex. Really, these statements up here are statements about H. It just so happens that H is the stabilizer subgroup is the group itself. So let's look at these key results. Okay. So just to remind you of the setup, I have my non-trivial dimension for my fusion ring, and it satisfies this very important quadratic relation just by looking at its dimension when I tensor it with its, or when I multiply it with itself. Okay. So the first result is not too exciting. Okay. It's the exact same result as the near group case, which is if I take a two-dimension fusion ring, if it's categorifiable, then it's categorifiable in a very nice way, this sort of pseudo-unitary with a typo in it, this sort of pseudo-unitary categorification. So really my notion of dimension is going to be essentially the same. I can just assume that it's this Frobenius Perron dimension. And this actually follows historically in the integral case from one of the very first papers in the subject. And for the irrational case, it was proven by a student of my advisor, Victor Ostricht, Hosea Thornton. So actually, the only real observation that I've made here is that in the irrational case, the invertibles act transitively on the non-invertible objects. That's all it takes to prove this corresponding fact. Now, our second fact, if I find a categorifiable two-dimension fusion ring such that D is rational, I get the exact same result translated into the two-dimensional quadratic relation that my constant coefficient, this S, has to divide the linear term in that relation. Okay. So that's actually quite strong. We've moved way out of the near group case. So if I pick a fusion ring that has two dimensions, I still have to have this divisibility condition between these coefficients on the nose. So if I start picking random two-dimensional fusion rings, chances are that's not going to be satisfied. It's not a very natural combinatorial thing. These categorifications are very constrained, even when you expand out to two dimensions. Now for one that involves our subgroup H. So this one was a little harder to translate from the near group case. So essentially, to prove that this underlying group was abelian for the near group case, you look at representations of the fusion ring, and you show that all the representations have to be one-dimensional. And that implies that your fusion ring itself has to be commutative. But that is not the case when you extend out to two dimensions. And so the statement is much more subtle. So the fact is if you take one of these irrational, so our quadratic is irreducible two-dimension fusion rings, and it's categorifiable, then the dimension of your irreducible representations are bounded by the index of the stabilizer. Okay. So on a representation theoretic level, our categorifiable fusion rings are very constrained. And you can see if G and H are the same group, you retrieve that original statement about our near group fusion rings. Okay. So this is much less strict than in the near group case. So you have a lot of fusion rings that have categorifications where D is irrational, but they're non-commutative. Okay, they have irreducible representations that are dimension 2, 3, etc. So you get a much larger set of interesting categorifiable fusion rings. And lastly, we have to weaken our last result because our subgroup H is not equal to G. And if we are in the case where our invertibles act transitively on our non-invertibles, and our two-dimension fusion ring is categorifiable, then the very small multiplicities, the ones that are less than our stabilizer -1, those must imply that our group, well, it actually doesn't imply our group is non-invertible, it implies that our ring itself is non-abelian in this case. Okay. So that should be noted. This does not imply GR is non-abelian. So why is that the case for the near group categories? Well, for the near group categories and rings, if our group is abelian, then the whole ring is abelian. And if our group is non-abelian, then the whole ring is non-abelian. It's an if and only if statement. But once you have a larger number of non-invertible basis elements, you could have that they don't commute with each other, even though your group of invertibles is abelian. Okay. So this is a big difference between the near group case and this two-dimension case. Okay. So all of these things follow in essentially the same way, but they apply to an incredibly larger set of fusion rings. Okay. But again, they also imply that basically any two-dimension fusion ring that you choose probably is not going to be categorifiable in any way. Okay. So, Elong, how long did you want me to go for?
I guess you can go. you still have 15 minutes. I guess that's fine. Because
Okay.
we technically will end at 12, but you can go on.
Okay. Well,
Yeah.
I'll breeze through this part because we've reached the point where now I'm going to be discussing things that are a little bit more technical and really would only be interesting to people who have looked at these before. Okay.
Mm-hmm.
So what's preventing these categorifications from existing? So basically what's preventing these categorifications from existing is one of the only tools that we have in this game, which is what we call passing to the double. So if I have a fusion category C, then I can construct from it another fusion category, which we call the double, the quantum double, the Drinfeld quantum double. There's lots of different names for it, the Drinfeld center, but it's this very highly structured, what's called a modular tensor category. And these fusion categories, they're basically just these associative isomorphisms sort of given life. These modular tensor categories are just incredibly structured. So they come with this modular group representation. They come with these ribbon structures, these braided structures. There's all sorts of different things that you can work with in the modular setting. And this passage, or one possible passage between these two worlds, is called induction. So I induct my fusion category to its double. And going back in the other direction, I'm just forgetting that I ever did that, and I have this restriction, or you can think of this as a forgetful functor, back to my original fusion category. So a lot of the restrictions on these categories existing are restrictions that are happening in this modular tensor category world, which is a whole nother discussion as far as what goes into that. So an ancient fact that basically everyone knew from probably the 1980s from mathematical physics and on is that if I look at the ribbon twists, with the full twists of my simple objects that appear when I induct my unit to the center. Again, this is very technical, so I apologize if I'm going over a lot of people's heads right now, but these ribbon twists are trivial, completely trivial. And this has been known for probably 40 years, maybe a little bit less than that. But what I wanted to do in my paper is, since I have a lot of other invertible objects lying around, the unit is just one of those, is I wanted to prove just a generalization of this fact for invertible objects. I couldn't find it anywhere in the literature, so I had to prove it. And what you would think sort of happens up to an extent. So if I take a fusion category with a little additional structure, I need it to be spherical for this double to be a modular tensor category. If I find an invertible object in my fusion category and I induct to the center, then basically these twists have sort of the same order as the original simple object. Okay. So this isn't to say that they're very small twists just by itself, just that they sort of all act the same when you take them to the nth power. So this comes in handy when this simple object acts with a fixed point. So if I take my invertible object and I act on all of the other simple objects in my category, if there's any fixed point to that action, then that implies that I have an nth root of unity. So the order of my twist on that simple object in the double for all of the summands in its induction are some nth root of unity, where n is the order of that invertible object. Okay. So this means as I go out to the center, my category isn't getting much more complicated. I had elements of order n down in my fusion category. When I induct up, I still see that n appearing in this double. So I'm not getting too much more complicated. So this is a fact that will come in useful, I think, in a lot of other situations when we're studying fusion categories. So very quickly, let me describe what this means for our near group fusion rings. So I'll breeze through this historical fact, but there's lots of different results about when these near group fusion rings are categorifiable that I've already discussed. In fact, for the non-abelian groups, if you include this assumption of unitarity, then technically they have been completely classified. And for that special case that your multiplicity is one less than the group, we also have a nice classification. But other than that, there isn't much. So if I start with an abelian group of invertible objects, there's basically only 3 abelian groups that have been completely classified when they're categorifiable. The first one was the trivial group 20 years ago when fusion categories were first being developed by my advisor, my PhD advisor. He also did the cyclic group of order 2 about 10 years later. So our complexity is ramping up quickly. And one of his other students did the cyclic group of order 3. And you can see that there are very few levels, there are very few multiplicities which are actually categorifiable. So my main application of all of these above results is by classifying all of the categorifiable near group fusion rings for elementary abelian 2 groups. So I wanted to find a family of infinite size where I could definitively say these are all of the near group fusion rings which are categorifiable. And the answer is kind of surprising. You would expect maybe by looking at this pattern here that as your group gets larger, you're probably going to find more categorifications. But for the elementary abelian 2 groups, for these reasons that I outlined above, you actually find out that it dies pretty quick. So for the Klein 4 group, there's actually only 2 multiplicities that are categorifiable. And for larger elementary abelian 2 groups, Tambari and Yamagami had already classified them. Only 0 works. So these infinitely large abelian groups have exactly 1 multiplicity, which makes it categorifiable. So the story is much more complex than I think we originally anticipated. I think most people anticipated that you would be able to categorify at least some multiplicities for all of these different finite abelian groups. But it turns out that actually, most likely as your group increases, I don't know, maybe order divided by the exponent or something, some complexity measurement of this group, you're going to end up with much less multiplicities that are categorifiable. So now that we're in the infinite world, now the stakes are pretty high. So hopefully the next results that come out are going to be maybe a complete classification for all of these finite groups. Who knows? But that's where we're looking for in the future. So I'll stop there. I have some open problems that I wanted to talk about and maybe a little bit about this proof, but I think I'll just leave some more time for questions. So thank you for listening. I'll put in a thank you for listening right here, since we didn't get to the one at the end. And I'll open up the floor for questions unless Elon has something else that he wanted to say.
Okay, let's thank the speaker for the great talk. So let me stop the recording first.